Hello and welcome everyone. Thank you for joining us today for the webinar about seismic attributes analysis. Before we begin the session, allow me to introduce about our company, which is 𝗦𝗲𝗶𝘀 Oil and Gas Solutions. We offer a wide range of specialized services, including technical reservoir studies, field development planning, reservoir static and dynamic modeling, technical support for academic research like PhDs and masters, assistance in writing technical papers and some publications, industry expert-led petroleum courses, mentorship, and specified customized training courses. So I would like to let you know about the future courses that 𝗦𝗲𝗶𝘀 will offer you. And here you can see in your screen, these are the incoming courses. We will be talking about applied seismic interpretation, borehole wireline image, processing and interpretation, and geomechanics principles and applications. If you're interested in one of these courses that we are gonna have and we're planning to have in the next months, please you can contact us to our WhatsApp line, or you can also follow us in LinkedIn, where you can also message us and ask for more information. Here in the top also you can see the prices if you're interested. So I hope we can see you in one of these courses. So today we are pleased to introduce our STEAM instructor, Dr. Ahmed. Uh, Dr. Ahmed, he is a senior geophysicist with over 17 years of experience in the oil and gas industry. He holds a PhD in geophysics with a focus on seismic reservoir characterization and has worked extensively across Africa, the Middle East, Southeast Asia, and North America. Dr. Ahmed has led and contributed to exploration and development projects with major international operators and joint ventures. He specialized in seismic interpretation, seismic inversion, and rock physics. In addition to delivering technical training and webinars, Dr. Ahmed is an active peer reviewer for petroleum geoscience journals, supporting scientific advance in the field. Dr. Ahmed, welcome to 𝗦𝗲𝗶𝘀 Solutions, and thank you in advance for your presentation.
Okay, thank you, 𝗦𝗲𝗶𝘀. I was trying to unmute.
Yes, thank you.
So thank you for a nice introduction and welcome to all attendees. So I hope my voice is audible now. Is it
Yes, it
okay?
is. Yes, we can hear you clearly.
Okay, so let me share my screen first. So also I hope my screen is visible.
Yes, however, we can see a box, like a black box in your presentation.
Okay. Okay, let me hide this. Okay, so now I think it's okay.
Yes, yes, it's perfect. So also before your presentation, um, for all the attendees, please, if you have any question or any requests for Dr. Ahmed, please leave them in the chat section to address them at the end of the webinar to avoid any interruption to our instructor. So thank you so much. And Dr. Ahmed, please, you can start your presentation. Thank you.
Okay, thank you. Okay, thank you. So today we are going to talk about the seismic attribute analysis. We are going through our webinar to talk about some topics as an introduction to seismic attributes. We'll see what is seismic attributes, the history of seismic attributes and development through the history, and the importance of seismic attributes, the classifications of seismic attributes, and some of the uses and the examples of some of the seismic attributes from published papers and some of the case studies. So let's start. So in order to say what is the seismic attributes, we have now an image. So how can we describe this image? In order to describe this image, you have this image, you have a man, this man having weird glasses. So he smiles. So of course he's pleased, and then he wearing some nice shirts. So from this you can describe some things for that person. So you can describe that he's having he has a gray hair. So baby gray hair. So okay, gray hair. He wear glasses. So poor vision means poor vision. It's okay. So during his laughing, so you can see his teeth. So it's okay. Teeth, good teeth. It's very good. No problems. So also the shirt is a good dessert. So from this picture, this is what can we describe. So after we describe, we are going to do our interpretation. So you describe something and then you go to do this interpretation. So this is what happened in the seismic attributes. You have attributes, then you are going to describe, and then you see that what is the indication of that seismic attributes. If he has gray hair, so maybe he's older, so he's very old. Then poor vision and also good teeth, good dresser. So absolutely, he has a lot of money, so he's rich, right? So this is our interpretation. So the seismic attributes or the attributes as a general is a quality which is associated with any person or anything or any character. Okay, like patience. Patience is like attribute of good teacher. Okay, so this is what the attributes. So moving to our topic, which is what is seismic attributes. You have now on the screen, you have two sections of seismic. These two sections, the same section with notations. So try to describe, when we try to describe this section, what can we describe? In order to describe, so we'll try to see, we have some of the colors. So this section, of course, is time section. You see, to the do the pointer. So now you see here, so this is time. So this is time section. Then you see some of the reflections. These reflectors having some different amplitude. This amplitudes is expressed by colors. So you have color of red color, and you have gray, and you have yellow. And this is expressed, of course, about the amplitude. Is it high or low amplitude? And then you will find that we have some sequences here, okay? And these sequences, you have like a sequence which is, you see my mouse here, this is like a grade incision or like an unconformity or major unconformity surface. So from our discussion now we describe like the amplitude. So we have some high amplitudes and some of the low amplitudes expressed by the high and the low of gray and the red and yellow also. And then we have some of the, you see here, in the upper part of the section, you have a high, you have a lot of peaks and the troughs, many peaks and the troughs. And then in the down part of the section, the bottom part, you have like very minimum numbers of peaks and troughs compared to the upper part. So we are describing now frequency. So the frequency, you have a frequency description here. So we described amplitude and we described frequency. Also, you have like some of the major surface of unconformity here. You have some of this response at the top of that or the base of that unconformity surface. Some is expressed by trough and others expressed by peak. So you have a change also in polarity. Some is peak and others is trough. So we described amplitude, and we described the frequency, and then we describe phase, and also we can notice that in time any reflector, which is a major reflector here, is changing in time. So also we can describe time. So describing these properties, this is the seismic attributes. The seismic attributes is based on these properties that we are described here: amplitude, phase, and frequency, and time. Okay. So we can answer now. Seismic attributes are the measurement of the properties that is derived from our seismic data, which is, of course, as we said, it based on time, amplitude, frequency. Okay, and also this is like according to Sheriff 2001. And another definition is it's a measurement which can help you to identify the features which is hidden in your seismic data. Another definition also is called it's tools to extract geology from your seismic reflection data. You see from the previous, you have here some reflections, which is peak and troughs, only peaks and troughs and colors. So you need to interpret this in terms of geology. You need to extract the geology from this. So the attributes is giving you this ability to see the same reflector, but you have some, this is high, is like having a bright spot here, a high amplitude here, which is disappeared here. So the bright amplitude becomes now, it's not bright. So of course it's express some changes in geology. Okay, so we are using seismic attributes to extract as much as information from seismic data. And as you can see here, this is a comparison between seismic cube in the 3D to the left, and to the right-hand side, you have an attribute. So this gives you the seismic attributes from the first glance here. You can extract some of the features which is hidden in seismic. You can see here, you have like, this is the hidden some of the hidden anomaly here, and this is hidden here. This can be revealed here. And also for the structures, you have a faults here. You see, you can sometimes you may misinterpretation of this fault, but in the attributes you can notice that you have some of the anomalies here, which is it's like an attribute, and another which is fault extracted by the attributes, and also here. So the faults and the diappear here are much clearer in the attribute display. So compare the right to the left, so you will find that the attribute display can give you some of the hidden information from the seismic data. So to go to the history of seismic attributes, it's of course a very, very long history, but we'll go very, very quick to that history. And you start with like it started with 1920. So from 1920, you can notice that from 1920 to 1960, seismic reflection data interpretation was largely a matter of mapping events, only mapping events. You try to find the reflector of the reservoir, you track the reflector, then you come up with a structure map. Okay, so you do like a structure map, time and depth structure map to determine subsurface geologic structures and the traps. Then in 1954, Rummerfield published a paper, which was a famous paper on mapping reflection quality to reveal subtle stratigraphic changes. And as it is very important, lenses is considered, this lens in 1982, it's considered, this paper which is published in 1955 for Rummerfield, consider this as a forerunner for the bright spot concept. So the bright spot concept started to be clear from that, and the changes becomes dramatically very, very quick. as in the recording, the digital recording becomes like available. So in 1975, all the digital, the recording becomes digital. So the quality of the data is improved. Recording of this data becomes improved. At the time when you have this data is improved, so you will have the opportunity to notice and to investigate the amplitude variation. So the first seismic attribute was reflection amplitude, which is, of course, still till today is very, very important attribute. This was like the change for the history of that seismic attributes. And then in 1976, the complex seismic trace analysis becomes available, which is published on SEG annual meeting in 1976 by Tanner and Sheriff. They introduced at that time 5 attributes, the complex trace attributes, which is instantaneous amplitude, instantaneous phase, instantaneous polarity, instantaneous frequency, and weighted average frequency. In 1980, a number of two-dimensional it becomes like the two-dimension attributes becomes available. So the continuity and the depth attributes also appeared in 1980. And then in the mid 1990, there were the 3-dimensionals becomes available, like continuity, discontinuity. So this took the expression worried by Stowe. So the excitement at the time that the brightest spot becomes like the amplitude, that's continuity, becomes very clear meaning, and becomes widely used. So the multi-attribute analysis also progressed slowly, but at late 1980 and 1990 becomes like the attributes of cross-plotting and the multi-attribute analysis, clustering, algorithms, all of these were employed. So according to all of this history, you have like some spots which is having like digital recording, and that the evolution of all of the seismic attributes becomes better after the digital recording, and then the frequency, reflection strength, seismic stratigraphy to yield some seismic stratigraphic features from the seismic data, and then inversion and the complex trace attributes, all of this till we arrive till the frequency and neural network analysis, of course, until our date now, machine learning and all the advanced in the seismic attributes. So this was like a quick overview for the history of seismic attribute. So let's move to the seismic attributes. As we said before, the seismic attributes, we use seismic attributes to extract more in geological information which is hidden inside the seismic data, and we address the time, amplitude, frequency, and the attenuation, and also the phase. All of these can be used either by using the stacked seismic data or the pre-stacked seismic data. Some of the information cannot be yielded from the post-stack only. You need to use the pre-stacked seismic data to yield more information, as we will talk in the next slide. The seismic attributes is very important. Why it's very important? Because when you start to drill a well in your field, so you have one well. So if you have this one well, or even if you have 2 wells, one here and the other to the other side of the image, so you have some properties which is you have measured in your well. You need to extrapolate and to see, is it continuous or this is discontinuous? So this can be tracked along all of the area or not. So the reservoir is distributed along your area, or still you have a limited area of the reservoir, and hence the hydrocarbon, of course. So the seismic attributes can be used to do that. So you can make the extrapolation, but not like an extra, the normal extrapolation. It will be like an extrapolation by using the attributes. So you can guide the extrapolation to some of the properties you have found. And for this section, this is an impedance section. So you can try to find like porosity. If you need to distribute the porosity, you can make like a relation between the porosity. So let me use this pointer. So if you have like from that drilled well here, like you have a porosity, and then you have also an impedance. So you can make like a relation between the P impedance and then a relation between the B impedance and the porosity, B in BHI, okay? So from this relation, you can predict, you will find that your points of reservoir zone here, giving you some points like that. So if you could like find that relation, you can find that which is the best relation that fits these points. You found that like this, which is linear relation. So you will find that, of course, if you are concentrating now, this line shouldn't be like that, because the acoustic impedance having a relation which is reverse relation with the neutron porosity. So I should make the line like that one. I will change that. I'll change that color. So the relation will be reverse relation. It's not like a proportional relation. So the relation will be like that, okay? And of course, should fit all of the points of the area that we have. So from this relation, we can take and make extrapolation for porosity based on the acoustic impedance. So we'll come up with porosity section or porosity 3D section. In this, you can distribute the porosity in that direction. So you will see if you have like high amplitude here. So this high amplitude can be also repeated along your area or not. So you can find that if this, so this high amplitude here can be also high amplitude here. If you use the extrapolation, the normal extrapolation, you'll find that the amplitude may be decreased and it becomes like decreased at this direction. So you will not find any attribute, any sweet spot here, and you may bypass some of the traps and some of the potentiality in your field. So we can use the seismic attributes to help us to extrapolate, but in intelligent way, some of the information from the well location to the others. And at that time, you are coming with the power of the seismic, because seismic is a 3D grid. So in the 3D grid, you have a power of lateral spatial distribution. But in the well data, you have high resolution vertically, but laterally you cannot do that resolution. So you need to use one of the tools, which is the seismic, which is having this power of lateral distribution. So you can distribute your thickness, porosity, and also the saturation of your reservoir. Moving to the second reason, also one of the reasons that we are using the seismic attributes to identify the structures that is in your area, the direction of the trend of the structure, and also you can use to infer some of the lithology, porosity, sometimes the fractures also, and the fracture density from the attributes. And also you can use this as a prediction tool to include also the geologic model as well as also the value analogs for your field. So you can identify, as is clear here from that one, some of the channel features can be seen here, very, very small, which is indicated by the yellow arrow. And some of the, is it like he has some amplitude, which is like he has doubt, is it like a joints, is it fractures? So because we are using the curvature attribute, so sometimes it yields that the negative can yield also the channels, fractures, as well as also the positive. So you can identify also some of the depositional environments for your area. Also, you can do some extraction for lithology and structure, and also the fractures. But of course, the fractures, we will talk about the fracture during our discussion for the curvature attribute. So from that attributes, we have many number of attributes. The attributes is very large numbers. So there is some classifications for seismic attributes to be able to use these attributes. we have the first classification here is that one which is organized all of these seismic attributes in 4 categories, which is qualitative attributes, then quantitative attributes, and interval attributes, and also you have the AVO attributes. The qualitative attributes, such as the coherency and also instantaneous phase, instantaneous frequency, also are very good to highlight some special patterns, lateral change, also like faults, phases change. Moving to the quantitative, the simplest quantitative attribute is the amplitude. So the amplitude, which is we like describe the peak. Is it the peak is very high or the trough is very high? Okay, as an amplitude, absolute amplitude. Okay, so this like also like the relative impedance. This is also quantitative attribute. And for the third category, interval attributes, it's like just using some intervals to do these attributes, maybe like this time interval, or maybe this like maybe an interval between 2 different horizons, right? So most of the seismic attributes can be extracted. This maybe we can say this is like a method of extracting seismic attributes. It's like interval attributes or like a surface attributes, okay? And also the AVO attributes. The AVO attributes is like the coming from the pre-stack data, like intercept, gradient, and also near and far amplitudes. Okay, so the first one is classify the seismic attributes to 4 main categories: qualitative, quantitative, interval attributes, and AVO attributes. Second classification is classified the seismic attributes according to the measurements that we are measuring from seismic, like time, amplitude, frequency, and attenuation. Okay, so they describe according to the basic seismic information. And you can see that you have like from time, you have pre-stack, post-stack, amplitude. Also, you have pre-stack amplitude. You can measure the amplitude from the pre-stack data, also from the post-stack. For example, from the amplitude for the pre-stack data, like AVO intercept, AVO gradient. Also for the post-stack, you can like reflection strength, reflection amplitude envelope. So all of this can be used by pre-stack seismic data or post-stack seismic data. The third classification also is categorize the seismic attributes to 2 main categories according to the attributes that we extract from the data, according to the data maybe that we are extracting, like post-stack and pre-stack. So mainly post-stack is having the post-stack attributes from the post-stack seismic data. I mean the data that we are dealing daily, and we do the seismic interpretation on that sections. So this is a post-stack. And this post-stack is subcategorized to like complex trace attributes, structural and stratigraphic attributes. I mean structural and stratigraphic attributes that can yield structural elements and stratigraphic elements. Okay, spectral decomposition and wave form classification, horizon attributes, and also relative acoustic impedance attributes. Of course, you have many examples of what seismic attributes. If you use any software, the practical software in the market having a lot of the seismic attributes, the most important thing is to determine which property you need to investigate. So what is the physical meaning of that property? So what is the impact on the seismic data? So you will be sure that you are going to extract some information related to that one. So if you are going to some of the amplitude change, okay, you are going to measure the change of the amplitude. So you can use like instantaneous amplitude. If you are trying to search for sound channel or stratigraphic body, so you are going to use one of that attributes, especially like the sweetness, or maybe sweetness is not written here, but sweetness, one of the powerful attributes for identifying some channels, it's here. sweetness. Yeah, we consider it as a complex, sorry, complex sweetness. So you are going to use the sweetness, regardless it is complex trace attributes or structural and stratigraphic attributes. You are going to measure some, you need to investigate some of the sand bodies, so you are going to use sweetness. If you are trying to see some of the faults, so you can use like some of the coherency, some of the depth, also the variance, semblance. So this can help you also identifying faults. So and so on for all of these attributes. For the pre-stack seismic attributes, according to the pre-stack data, you can use from the pre-stack seismic data, you can generate the intercept volume, gradient, curvature, near and far stacks, Poisson ratio, fluid factor, and even elastic impedance, extended elastic impedance, and lambda rho. Of course, some of the properties like geomechanical properties, which is brittleness index, also can be used to guide the interpretation of the fracture. So many seismic attributes, as we said before. And also the last classification here, we use here in our presentation, that classify the data into the seismic attributes into geological, geophysical, and mathematical seismic attributes. Of course, starting with the geological, this is the most useful attributes. It can help you to reveal some structural features or stratigraphic features or even lithological features. Structural features like the depth, the azimuth, curvature, discontinuity also. For the stratigraphic, it can help you to identify some of the reflection pattern, the reflection spacing, and the parallelism. Is it parallel, not parallel? So the surfaces and the relation of each surface with other one, the down lab, truncation, and so on. The lithological also can be used to reveal some information about porosity, density, also fluid content, and the sand percent or sand net to gross ratio, also the impedance. If you notice that from our talk here, so the structural and the stratigraphic, the features can be healed here by using the post-stack seismic attributes. Why for lithological, it goes for the very detailed, like the lithology and some of the porosity, density, fluid content. So that lithological cannot be done with using post-stack seismic data only. You need to use the pre-stack seismic data. So you will have the P wave, S wave, and density. From that three parameters, you are going to generate a lot of seismic attributes, which is maybe sensitive for your features that you are trying to investigate in your area. So the most important is the geological attributes. Then less important, which is geophysical, which is this geophysical, like we can say it's intermediate important, like you can record some of the properties of the waves and wavelet also. It's include the amplitude, phase, frequency, bandwidths, and also they must be inverted. These geophysical attributes, they must be inverted in order to obtain a geological information, useful geological information. The geophysical attributes also is like straightforward to measure. So you can measure that, you can generate a huge number of geophysical attributes, but the only matter or the most important thing is to relate this result with the geology. You need to relate and to understand the anomaly that you have got from these seismic attributes to the geology of the area that you are investigating. Okay, so and the last one, which is mathematical attributes, this is like the least useful one. it's like records the averages and the minimum, maximum. You will find that like it's like a mathematical operations. You use like the average variances between some cubes. So like a statistics of seismic data. So this is purely mathematics, which is less important or less useful or less to get some information from it as it is a mathematics. Okay. So moving to having some of these attributes, some examples, and to some definitions for that attributes, and how can we use these attributes? Is it important? And some of these examples can show us what is the structural or stratigraphic features. We can see here that the first we will start with the slope and the depth and azimuth attributes. For the depth and azimuth, you can use the depth and the azimuth together. The depth is giving the reflector dipping on the horizontal, and then the azimuth giving you this dipping on that direction. So the azimuth for the direction and depth for that inclination. So you can use together to quantify the reflection orientation or the dimensions. Okay, so we use it to have the these two words like slope and dip to be used commonly as one term, or like we use it as synonyms. But unfortunately, it's not like that. There are some differences between slope and the dip. If you are concerning with the seismic in-depth domain, the slope becomes like in this here. You will do that. You have this is a distance, and then you have the horizontally, and then the vertical will be, sorry, we have, okay. So you have, this is like a distance, and then this is the depth. So when you are dealing with the depth data, the slope will be dimensionless. So no units, because you have distance over distance, okay? So you measure change in that distance vertically to the distance horizontally. So it will be dimensionless. And then if you are dealing with the time data, it will be different. So for the slope, it will be like maybe you have a positive slope or negative slope, okay? And each one is giving you the direction of the inclination. And for the time data, the slope becomes the reverse of that units, which is becomes like the apparent velocity. So the slope in the time will express a velocity, okay? Inverse velocity, which is will be like millisecond per meter. Okay, so we can say that slope is a property that is like geophysical, like we had described before, and the depth can describe a geological property. So looking to that figure here, we have two figures. The first one, like to the azimuth combined with depth, and the right one is the azimuth. So you can see that the right one is azimuth, having some of the change of the azimuth here, and this is the scale. So you see that you have some of changes of the azimuth here. So try to implement this with the depth also, as we said before, depth and azimuth. So it will give you, you see here, this is like after you blend the two attributes, the depth and the azimuth, you can identify now some of that features, which is like this feature was here, it's okay. But you see some of that features here, some of these features here, very small features here, you have one here and the other one here, and this is the third one, fourth one. All of this is also contained here, but it's not clear like that we have from blending depth and azimuth together. So the seismic attributes also can be blended together. But we can use one attribute, and also we can use more than one attributes to yield more information about the area. Moving to the curvature. The curvature is most interesting also, as the curvature is refers to the of the depth and azimuth. Okay, so the change of along the seismic reflection or horizon can guide you to some information. the curvature is, we said that the curvature is very important, and we consider here Lysel in 1994, it considered that this is very, very important because it is associated with fractures. So why we consider that the curvature is very is associated with fractures? Although you know that the seismic resolution is like cannot go for very small details. So why we are associated the curvature with the seismic fractures? Even we are not going to have all of this information, very, very small change in that information from the seismic resolution. Seismic resolution cannot go for that, small details. So the answer is the fractures, as you know, the fractures tend to be developed geologically in the folded layers. So if you have a folded layer, it will be like having a fractures, tend to have a fractures. So the brittle rocks, it will be like at the top of the folded layers will have some of these fractures. So the folded layers itself is a fracture, is a curve here. So you see, so you can measure curvature from here. So this will be like a positive. So at that, we assume that the fracture tended to occur at that anticlinal tops or synclinal bottoms. For that reason, we associate fractures with that. So we use the fracture curvature attributes to measure the fractures. Okay. We can consider that it's not indicate that the fracture is exist or not. Okay, as we said, it's a geologically possibility to have a fractures at these locations, but the strong curvature does not indicate that you have developed in that areas or that zones. Okay, and the curvature also cannot image, as we said, the fractures directly because the problem of the size. This is the size is below seismic resolution. So the curvature can reveals the channels, anticlinal tops, and also can reveal the synclinal bottoms. Okay, so all of this can be yielded using the fracture, the curvature faults also, because you see here in faults you have some dragging here. So this dragging is giving you like that synclinal shape, which is will be a negative curvature, but while on the anticlinal it will be like a positive curvature. So you can also determine that the fault or the structural position, the structural features, and even the stratigraphic features like channels, the side of the channel give you the positive curvature, while the center of the channel can give you negative curvature. Okay, as we can see from that. But if you are going to try to investigate about the fractures, this is from the post-stack. Now we are talking about the post-stack seismic data. If you need to go further and to try to find the fractures, of course, the pre-stack seismic data can help you more to get a lot of information about the fractures. As the pre-stack data having the B impedance and S impedance, implement the B impedance, S impedance, and density. So all of this is having more information which can help you to identify the fracture. And for example, if you have the pre-stack seismic data, you can use the pre-stack seismic data to do the pre-stack seismic inversion. You will have the P impedance, S impedance, and density. From those three main results of the pre-stack seismic inversion, you can calculate a lot of properties like a Poisson ratio, and also you can calculate some of the brittleness index, 3D volume. So you can use all of these attributes to predict the fractures, even from if you have drill wells in your area and you have some of the FMI logs. This FMI logs, you will have like fracture intensity. If you could get the fracture intensity log, you can use this log and make a relation between the fracture intensity log and then the some of the inversion results by using the cross plots. And then from that cross plots, the relation can be applied to that 3D cubes, so you can predict and you can find the distribution of your fractures and the intensity of the fracture. You will find that this area having more fracture intensity, so you are going to drill your wells here, especially in the hydrocarbons, in the carbonates. So it depends on what is the reservoir you are investigating, and also what is the property you need to follow or to see. Okay. So moving from the curvature to discontinuity. So the discontinuity is like a measure of the amplitude and the phase consistency. The continuity is measuring the degree of consistency of the amplitude and phase, both amplitude and phase. And the seismic discontinuity refers to the breaks in the continuity of seismic reflection, which is good, of course. These could be like this continuity could be stratigraphic or structural breaks. Okay. The discontinuity is often called a coherency or similarity. We called it like coherency or similarity. It depends. So you'll find that sometimes it called like coherency and others like similarity. Okay. So similarity based on mathematical property, and coherency suggests geophysical property, and discontinuity, of course, based or preferred on the geological property. So discontinuity of any the reservoir unit or the structure that makes that one. So the discontinuity can reveal the breaks, and these breaks, which is caused by the faults, diapir, and the bench out also. And of course, sometimes this cannot be related to the geology, maybe noise, maybe some artifacts, if this is not eliminated well in the processing. Okay. So the discontinuity also, you will find if you have the discontinuity cube, this discontinuity cube will be like having a values from 0 to 1. So it measures the continuity. So perfect continuous will be 0. And when you have some of the discontinuity, it will be 1. Perfect discontinuous data will be 1. Okay. And then you have the range between 0 and 1. So in order to know how the discontinuity are calculated, when you start with that trace x1, you have the adjacent traces here. So you're trying to see the change of the amplitude and the phase from that x1 to x2 and comparing also to x3. So you will find that change by using a cross correlation. You can identify that change. So if you find some changes here, it will be marked by 0 or 1. If you have the similarity, it will be 0. If you have dissimilarity, it will be 1. So we'll identify that you have something here which is separate this one about this trace. Okay. So we consider that also is the most important 3D attribute, as it can give you some of the identification of reservoir boundaries, and also if you have a structural trap, 3-way or 4-way deep closure, you can identify the actual position of the fault, especially if you are going to target the near location to the fault. Okay, this is an example from the seismic the discontinuity attributes. You will have here like seismic section, and then this is the original seismic section, and then here this is one of the discontinuity, but we didn't consider for the depth correction here, but we considered for the depth correction at that section here. So you can see that some clear information about the faults becomes very clear here in C figure compared to the B figure, because we used some of the correction for the depth. Okay. And also for the time slices here to the right, this is a comparison between these time slices using the some of the methods to calculate the discontinuity attribute. One of them is like the mathematical methods like correlation, semblance, and also weighted covariance and weighted correlation. So you see the strong discontinuity are expressed by the red color, while the similarity, it will be like that white. So you can find that you have some of the channels here you can identify. You see here, maybe this is a channel here, and then you have some of the structures here, you see here, and then you have here also semi channel is here also. Some of the areas becomes more clear, others not. You see here also. So the difference is very small. So you can use also to identify, and also different calculations methods will give you some changes, very small changes, but still you will be able to identify that features. One of the also the seismic attributes that is based on the amplitude, we have here time slices. We have two examples here. This is the same area also. This is examples from the same area. This is published also in the post-stack seismic attribute handbook. And you can see here, this is the structure map for the surface. And then they extracted some of the horizon attributes with some of the window length. Then they calculated the shaded relief, and then depth, and then the azimuth. And then here we have the edge detection attribute also, using the smooth, the unsmoothed horizon, and this is smoothed horizon. So also you need to take care when you have smoothed and unsmoothed horizon. Here, this figure here, which is highlighting by the laser pointer, it's using the unsmoothed horizon, and then that one using the smoothed horizon. You can see some of the features, this becomes not clear, like this feature you see here. So maybe we have some faults here. This is minor fault, but you cannot find this, you cannot find it clearly like that figure here. And also some of the features here becomes not clear like what we have here. So smoothing also of the horizon can affect your attribute result. So you need to be careful when you do some of the smoothing, even for the structure horizon. Okay. And then you have here the curvature, and also this is maximum curvature, and this is minimum curvature. So you can also identify some of the features which is maybe we missed at that one. Some of them becomes more clear, and others becomes not clear. Moving to that figure here, you will find that the amplitude attribute also, which is for the same area, but we have the window, which is 40 milliseconds, and we shifted this horizon downward 100 milliseconds to find the reservoir and to see the reservoir properties. So here, this is the original seismic data, and then you have the peak is the blue and the trough is red. And then they try to extract some of the attributes along that horizon. So they come up with, you see here, if you compare this figure here, which is RMS amplitude, root mean square amplitude, compared to the original seismic, you'll find some of the high amplitude here in seismic. But you see here, this high amplitude can be identified more clearly using the RMS. So you see, maybe you have a channel here, and you can see that channel, and this is change and meandering shape, right? So you can find this from the attributes, can give you some of the details which is maybe hidden in seismic because of the wavelet effect. So you can go again also for the another one, which is AAA, which is average absolute amplitude. Average absolute amplitude here also can yield some of this information here, as you can see here. And also for the average peak amplitude and average energy, maximum amplitude and minimum amplitude also, and arc length can give you some of this information. You can see some changes for this slice to another slices. So from attribute to another attribute, some of them can give you some edge enhancement or detecting that edge clearly, and the others maybe to some extent. So you can use some of the attributes in order to identify your reservoir clearly. So this is one of this is most of the seismic attributes, one of the common seismic attributes that we can use also. Root mean square, average absolute amplitude, and also average peak amplitude, maximum amplitude, minimum amplitude, and arc length. Moving to another one, which is sweetness, seismic attribute sweetness. You can find that the sweetness, we can define the sweetness first before we go to the example. The sweetness can help you to identify the sweet spots that can or that bearing oil or gas. So the sweetness is an empirical attribute that is designed to identify the sweet spots, because this attribute combines the effect of the amplitude and the frequency together. So these two parameters, amplitude and the frequency, usually they affected by the presence of hydrocarbon and or the gas. Okay, and also the reservoir quality also is affecting the these properties, the amplitude and the frequency. So you can use sweetness to have this. So the sweetness represent instantaneous attribute in which the response of the amplitude and the frequency also can be combined. And these attributes can give you a very good indication to possible lithology and like poor fluid within the lithology also. And as you can see from that example, we have here this seismic section, and this seismic section having like this incised valley. Unfortunately, I don't have this seismic section uninterpreted. So if you try to imagine, you can sometimes you miss this, you miss to make this interpretation for the incised channels. So this incised channels now it's interpreted, and you have the frontal splay. So try to extract the sweetness for time to take time slice or horizon slice here. So this will be like the result here. So you can identify that it's very, very clear. You have this is incised the valley here, and also you have a fault cut here. So you can see much more clear image for the incised channels, stratigraphic features, structural features, and even within the structure, the stratigraphic features, you can find that you have some of the amplitude which is very high, and some of them is very low. So it means express some of the change of the quality or the thickness of the reservoir. Okay, so the application of sweetness can give you some you can use to delineate the positional elements such as channels, frontal splays, and also you can use for the internal heterogeneity of the reservoir. Of course, it depends on the data and the case that you are using, the noise signal to noise ratio, but it can give you some information about that. And also from the geological information that you have, you can make a correlation with the results that you come up with, the slice, and also with the geological information that you have. This example from the Gulf of Mexico. So you can, this is published by Hart 2008. So also you can use the sweetness to yield of some of these feature some of these attributes. Moving to another attributes, which is very common, which is spectral decomposition. The spectral decomposition attribute is now we are transferring from amplitude, phase to frequency, moving from amplitude and phase to frequency domain. We transfer to do the spectral decomposition. We actually transfer or transform the data, the seismic data, from time or depth domain into frequency domain. So the spectral decomposition apply time frequency analysis, and this time frequency analysis gives us a result which is set of slices, maps of relative strengths of different frequencies. You will have maps of different frequencies, each frequency having the relative strengths for each one. So you can use to investigate some of the hidden features, which is maybe you cannot identify using the amplitude and the phase. Usually we use the RGB blending method, red, green, blue blending method, to blend some of the different frequencies. You have some like that one, and the result will be like that example here. If you have like your area, so you have the seismic cube, then you are able to investigate 125 frequencies. Each frequency can be represented by a slice. So you can extract the frequencies, which is giving you more geological information, and then you can blend. We use red usually for the low frequency, and then green for the mid frequency, and the blue for the high frequency. So when you have these three frequencies, it's like the red and green and blue, when they intersect, as you see here in that figure, when they intersect, they will give you white color. And then this white color indicates that features which have equally strong response at all frequencies. Okay, so all frequencies having the same response, so this will be like such a bright reflection. Okay, so this can guide you about that, which is frequencies that is reflecting this feature of geology. And look at this example. You have this seismic section here, and we have a time slice here, and this also the same preview. So time slice here for the RMS amplitude, and you have seismic section here. You see, this is a channel here, and this width is like 3 kilometers. So you can identify that channel here from the RMS, right? And then go to for that part using the reflection strengths. Some of this data can be like, okay, clear, but then you can go for that here using the 10 hertz, 14 hertz, 19 hertz, 26 hertz, 37 hertz, 51 and 70 hertz. According to each difference here, this is like containing the 10 hertz and showing you the representation of the 10 hertz along this area. And also this is showing you the representation of 51 hertz. Is it represented here by high values, here high values, low values? So you can identify that. You see here, it's very clear here for 51. So you can use 51, and also you can implement with different slices to give you the, and also use a different color to give you like the RGB blending method. So you can use also this, whatever you use, like this slice. Also you can use the blending method, will give you the good indication for your reservoir. So another example here from Northwest Shelf, Australia, and this is adopted from OpenDetect webinar. You see here, you have the seismic here. This is seismic atop of the reservoir. So you can see that you have high amplitudes, and you have some of the features which is here. So maybe you can interpret this as some faults here, others here. Also have faults here, and there. So some of the faults, the area is faulted, is too faulted here. So this is a map view here for the top of here section view. So from that, you can see if we extracted 10 hertz using continuous wavelet transform, you will find that you see this feature here. It's a channel. See, cannot be fault, right? So this is a channel. So it's becomes more clear when you use a frequency. So now we are in the frequency domain. You can find that this is like a channel here. So this channel is here in this is the level of the channel. So you can try to find if this is a channel, direct channel or not. But if we are using the interpretation, we may misinterpret this channel. So we put a fault here, fault there, and the other fault here. So we'll make some of the faults. So this channel is hidden, but I will show you some of the zoom section for that channel. So we can track this channel, and then you see here, this is like a zoomed section from this part here. So we may misinterpret this one to make like a fault here and another fault here. So this is may come up with neglecting the channel. But you see here, the spectral decomposition can yield this channel and can capture this channel. So you can identify that the canyon here and also the channels inside that big canyon. Another example for spectral decomposition also, and the uses for identifying the stages of the development of the channel system, complex channels. So you can see that here, the first, this is like spectral decomposition map, and you have this spectral decomposition to the left, and then also using the blending, RGB blending, and then to the right, for each figure, you will have the overlaying some of the sweetness and water saturation to highlight the sand channels, and inside the sand channels also you can highlight the saturation. So not all the sand channels will be filled with hydrocarbon. Some of them, of course, will be filled with water. So you will be able, like that part, you see, this is a channel, right? So this channel here can be yielded from the spectral decomposition. While when you use that one here, you will find that a slice here from the sweetness, but because we use the water saturation also to implement with the sweetness, you see this part becomes not like bright. So because sometimes maybe this is, as a result, of course, it is like water bearing, but others part you see still having the bright. So this channel is filled with hydrocarbon, okay? And this is a geological schematic block diagram for the stage of that channel. This is the first stage. Second one, you can see this one, also the spectral decomposition, and this is a schematic for this stage 2. And also we have here the sweetness blended with the water saturation. So you have this blend also can help you to identify the, as we may say, the saturation. So saturation of sand can be guided also from that one, and also the third stage here, and also the fourth stage here, which is the abandonment stage. So you'll not be able to identify anything here. Okay, so this is also can give you very small details about that small details, the changes, very small changes also you can go beyond seismic and go for the frequency to identify that it changes. So moving to the another attribute, which is seismic inversion. The inversion is one of the attributes. As you remember, we can classify this as a pre-stack seismic attributes or post-stack even seismic attributes. So this seismic attributes, inversion is one of the seismic attributes, but it's commonly used as we commonly use focus for the seismic inversion separately, because having a lot of details that we can yield that we can use. So the seismic inversion, what is seismic inversion? If we need to have a definition, seismic inversion we use to create a geology model from the seismic data input. As you can see from here, you have this section here, and this section having this reflector, right? So if you are trying to pick this reflector, you will use to pick this reflector right, like that one. So you can go for that reflector high and low, right? But you see here, this is the inverted section for the same section at top. So you see, you have some of the amplitude change here. This amplitude change cannot be identified from the seismic data. When we remove the wavelet effect and make the inversion, we will be able to see these differences. See differences here, low amplitude, and this is high amplitude, you see? So these differences cannot be identified. And even you see here, the amplitude here cannot be also identified here. You see, so this is very important. When you do seismic inversion, it gives you acoustic impedance. So the acoustic impedance from post-stack inversion can give you also more information. Whatever this relative acoustic impedance or absolute acoustic impedance, it can gives you this information. So the benefits, you can use this as a petrophysical properties. You can derive petrophysical properties of the rocks, and also you go for high resolution rather than the seismic data, and the lateral heterogeneity you can identify easily, and also lithology prediction can be used. But remember, the lithology prediction, as we said before, you need to use to implement the pre-stack seismic data. So as a seismic inversion, like just a quick look for that one, we have forward and backward modeling as an attribute. This is that we have in the section of the seismic. This is the seismic, comes from that one. You have the earth, and then you send the waves from the source of the waves. Then you come up with the seismic section. When you have the seismic section and you need to retrieve the geology, you remove the wavelet. You remove the wavelet. So we do seismic inversion. And then you will come up with the acoustic impedance, which is the density multiplied by the velocity. So it expresses the properties of the reservoir. So when you have acoustic impedance, you can try to estimate, is it this model, can be this model, or can be different models, okay? So this is from acoustic impedance. When you use pre-stack inversion, of course, you will have some of the information which can be more useful than the post-stack inversion. Of course, it depends on the data that is available. And for the seismic inversion method, we have like seismic inversion method can be also that we have the input data. If we use the mathematical approach, we can classify to deterministic and stochastic. And to see some of the examples of the inverted volumes also, you have this input seismic, and then you have this model-based inversion. So you can come up with some of the, you see some of the amplitudes here, some of the acoustic impedance here. You see this one cannot be identified. You see, you can try to find here, but you will find that it's in this location here. You have peak or trough, which is continuous. But when you have the inverted section, you can identify that this changes. You have some of the changes here, and even the reservoir here also can be identified. You see some of the differences here, which can be tracked laterally also. This is a colored inversion, which is also having some of the relative acoustic impedance different than the first one, which is absolute acoustic impedance, but also gives you some of the details. You can see some of that amplitude, which is stopped here and becomes lower amplitude here. And also you see this part here, which is corresponding to the gas zone for the reservoir. So you can track this also properties from the seismic data. Also, you can use the pre-stack data to make some of the to make it short and to not to make it a long webinar. Like the reflectivity, you can try to find that the classes and you can have the angles you have to the far, and then you can measure the amplitude at top the reservoir. Is it the amplitude is decreasing or increasing, or even you have a change in the phase? So this can be classified also into different classes. These different classes can be used also to track your reservoir, and is it also you will find that some of these properties in the distributed in the area or not. So the pre-stack, as we said, and if you remember, you can use the pre-stack inversion to do some of that also as an attribute. You can use the B impedance attribute, and also here, this is VBVS section. You see the reservoir here is having some low and some of the high amplitude here, which is high acoustic impedance, and also for VBVS, it's low VBVS ratio. So you can use to track your reservoir. You can make a cross plot, and then you can use that values of that reservoir from the well log data, guided by the well log data, to identify that part of the gas bearing zones. And then when you determine that gas bearing zones, you will be able to distribute that in your 3D seismic area. Then you will be able to identify the gas bearing zones. You see, you can identify the gas bearing zones laterally also, and you can try to investigate for that delineation of that reservoir. So by the pre-stack seismic inversion, we reached to the end of our webinar. So as the most advanced seismic attributes, you can use the pre-stack seismic inversion. So it can yield a lot of information that is hidden inside the seismic data, which is you cannot be also, maybe you cannot get from seismic attributes, the post-stack seismic attributes. So as you go for further investigation, you need more not for sophisticated, but it takes long time and also require more data to be available, like BNB, the angle stacks to be used also to do the pre-stack seismic conversion. And also for the well log data, you need to have the shear sonic and the P sonic also to be recorded in the well to be able to do that also using the well log data. So finally, thank you for your listening and attending the webinar. It was like a very quick look for the seismic interpretation, seismic amplitude analysis. And I hope you interested in the webinar. And if you have any question, I will be glad to answer your questions.
Thank you so much, Dr. Ahmed. Yes, we have some questions in the chat session. So I don't know. Yes. So maybe we can read it and answer it. Thank you so much.
Okay, I'll try to open the chat. So let me open the chat box. Okay, so starting with how do we understand the unconformity from seismic section? It's like the unconformity you can see from the seismic section. If we go for that, I'll try to go for that slide. I bet it was like that section. Yeah, the unconformity here, you can see that we have the major change here. So you will find that you have a high amplitude, which is expressed that you have differences between the upper and lower layer. So these differences in density and velocity, it causes some of the differences. These differences will give you a high amplitude reflection. So you will be able to identify this is like major unconformity surface. And you can see also, you see, it's continuous here, like that one. So it's not like parallel like that one, but it's like, you see, it's cutting through the reflectors, and you have some of the layers which is truncated on that one and the on lab on that reflections. So on that major reflection, so you can identify that this is an unconformity from seismic. Okay. What is the best seismic attributes practices for imaging subseismic resolution features? I think this was in the beginning of that the webinar. So the attribute, we can use many attributes. As you mean the vugs and the fractures, I think I answered that one by using the fracture density. If you have the fracture intensity log, this is like the most we can use. We can use the pre-stack seismic data. If you try to use from the beginning the post-stack seismic data and you have post-stack only, so you are going to use the to see the curvature and also to see the discontinuity attributes. But curvature also and discontinuity can give you some, especially the curvature can give you some information about that, but of course still in limited. And as I said, the curvature is like an indication or give you the possibility of having these structures at the possible location that have anticlinal shape or synclinal bottoms or channels. So we are going to investigate the anticlinal shapes to see that these locations, when we determine this location using the curvature, we assume that this is the most place that we could identify some of the fractures that could be present in that location. For that reason, we're using the curvature. But in order to, we can say that this curvature attribute will be qualitative analysis. If you are going to the quantitative analysis, you need to go for the pre-stack seismic inversion and do the pre-stack seismic inversion, do some of the calculations from the result of the pre-stack, like density and the S impedance and the B impedance. We can, from these three output from the pre-stack inversion, you can come up with some of the geomechanical properties like Poisson ratio, brittleness. So the brittleness give you that high brittle or low brittle. So we can find that the expect where is the fractures that you can find. Okay. And also you can use the FMI log and make some relation between the FMI log, the result from FMI, the density, fracture density log, intensity log, and then you can make a relation between this one and the results of the seismic inversion, especially Poisson ratio and the Young's modulus, and also the brittleness, and then you can have a relation which enables you to do some of the distribution of the fractures. Okay, I hope this answers your question. Moving to the other question, can seismic attributes be applied directly on depth domain seismic data? Yes, seismic attributes can be applied directly on depth data, or the data need to be time domain. See, some of the data need to be on time domain. Some of the calculations need to have time during the calculation. And I will give you example, like the spectral decomposition. Spectral decomposition is addressing the frequency, right? So in depth domain, you will not find the frequency. And also the data in depth domain will suffer from the wavelet distortion, because you transfer the data in order to be converted from time to depth, it will be using a velocity. So this velocity may distort the waveform. So the waveform will be distorted a little bit. For that reason, the depth domain will not be preferred. But I will tell you, a lot of trials have been applied for depth and time domain, and also they yield some of these information. But take care during the seismic in time domain. Of course, you can make it like you can extract wavelet, but in the depth domain, it will not be like a wavelet. You can call it as wave number, not wavelets. Okay, some of these small differences will be noted also. Okay, but you can try to do some of this information. Of course, these attributes, you will come up with a lot of results. Could please make available the record slide to attendees? Yes, of course. The meeting is being recorded by by 𝗦𝗶𝘀+, and then after we finish, of course, they will make it available for all of the attendees, and the link I think will be shared for your group. Okay. Can seismic inversion be classified as part of attribute analysis? And lastly, does seismic training advertised before the webinar session? Will the training be focused strictly on attribute analysis? Yeah, if you are talking about the applied seismic interpretation, it will include seismic attributes for one day, but will not be go for the course is not focusing for attributes only, because you see, if you are focusing for attributes, it will take a lot of time. Even we try to finish this webinar and not to make this a long webinar to be good for the attendees, but this will be like, we may address another course concerning with seismic attributes only to be also implemented, but the upcoming course will have the seismic attribute as 1 day out of 5 days. So the seismic attributes like RMS and the sweetness are very sensitive to tuning and cool effect. How to use this attribute in case there is thin reservoir and cool musket? To use a seismic attribute like RMS and sweetness, of course, we try to, of course, the cool effect will have some major effect, but you try to first try to isolate the zone of interest that you are using, try to avoid that one. And of course, you will have like before you start to do the seismic attribute, maybe you can go to make like some conditioning for the seismic, try to do spectral balancing and spectral balancing analysis first. And then from the spectral analysis first, you can try to enhance the spectrum of the seismic data and make the spectrum more flat. So you will have the amplitude is more, you will find that some of this is more representative. It will be like more clearer than the original one. So I think you try, of course, you have the data and then you need to deal with the challenges. So try to make some of the conditioning first, and then try to do that analysis, especially and carefully to do some of the analysis for the window and try to find the frequency content at that window. And then we try to, even for the spectral decomposition, you try to find the window and the dominant frequency, and to try to not miss that one, because yeah, the effect, the tuning, of course, will affect your result. From which software we can generate this seismic attribute data? Seismic attribute data can be applied using many softwares. I think all of the softwares that is in the market now is doing a lot of attributes. Sometimes you found some softwares is perfect in doing some of the attributes, like spectral decomposition. You can do with I prefer to use OpenDetect to do spectral decomposition rather than some other softwares like 𝗏𝗏𝗀 or any other software. Of course, I'm not intending to make it like an advertisement for any software, but just for as a scientific purposes, you can use some of the softwares like doing some of the spectral decomposition, and others for doing seismic inversion, and others for doing modeling. So it depends on the software and the capability. Some of the softwares having capability to do something, others not. So you don't have a software which is having all of these capabilities. You don't have the power software, Superman software. So what moving to another question, what determines bright spot, flat spot, and dim spot in seismic attributes? And what type of hydrocarbon presence do they reveal or indicate? It indicates that we have a hydrocarbon, okay? And let's see that, of course, if you try if you have the data and you have the bright spot, you try to, in order to be clear, to have 5% of saturation of gas in your reservoir, it will give you a bright spot. So whatever you have 90 or 5%, it will give you a bright spot. So bright spot can also trick you because it having a residual gases. So if you have a bright spot, of course, you are not going to drill this bright spot, of course. You just need to make sure that this bright spot is actually having a hydrocarbon saturation. For that reason, you are going to compare, if you have another wells which is drilled in your area, to compare and to see the class of that. You can try to see the class of the hydrocarbon, and then from that drilled well, and then you can generate intercept and the gradient, and then you can try to make to find the class of that EVO, and then try to track in your area. This is one thing. Others also, you need to be careful, because this brightness may be according to not the hydrocarbon even, but maybe according to the tightness. If you have a tightness, it gives you also bright spot, may give you bright spot. So you need to be careful. Just not bright spot, you are going to drill as it is having a hydrocarbon. So it need to be like having some of the investigations and doing some of exercises and investigate your data and integrate a lot of information, even the positional model of the area, the value current. All of this geological information can give you, can be addressed in this area or not. So I mean, you need to integrate a lot of data. Even the seismic, you need to do more exercises to see the AVO class of that reservoir and the track. If you found that bright spot, the other bright spot is that corresponding to that one. it may gives you some of the results that you need to go further for some of the investigations. So it's need more investigation, of course, and then you can see from the seismic data itself and also from the inversion, you can get also that responses of that hydrocarbon, as we seen from the examples that I have attached at maybe the last slide or the slide before. Here, like you will have that the hydrocarbon will, you see here, this is hydrocarbon here having a low density and also having low velocity, wave velocity. So it gives you like, giving you an impedance which is different than the corresponding or the nearby impedance or rocks. Cannot see your screen. Oh, yeah, sorry. The last slide that I'm talking about, that one, it is like the to answer the question of, I will share it now. So I hope my screen now is visible for you. So in order to, I was answering about the last question about that, how can we identify that the bright spot, dim spot, and the flat spot? Of course, from seismic section, you can identify, and then also from the impedance itself, when you do the seismic inversion, you will find that the impedance of the reservoir is different than the surrounding rocks. So also you can identify, and even from the cross plots, from the well-log data itself, when you do the cross plot from the well-log data itself, you can identify that, you will find that this is the anomaly, or this is gas bearing rocks here. So you can isolate this one by determine this by using the that shape, oval shape, and then you can apply that on the seismic data. When you invert the seismic data, we move these limits from well-log data and apply to the result of the seismic inversion results as a cubes, then you will come up with this determination or identification of that reservoir. So let me check also the questions, but I need to stop sharing. So okay, screen is blank. Yeah, please show the screen. Yeah, sorry. Is it necessary to do seismic data conditioning? And is this part of attribute analysis? Yeah, if you could do some of the conditioning for the data, it depends on the type of the data that you are trying to investigate. This will give you some good results. Sometimes it depends on the data. Sometimes you are using data, and this data having like acquisition footprint. This acquisition footprint is like giving you like lines by in and cross lines. So this can affect your attributes and sometimes can give you false results. So you need to make some filtering for the data or tell the processing center to eliminate this acquisition footprint. Okay, so yeah, the answer is yes. You need to make some of the conditioning and try. You will do the conditioning and use the conditioned cube and unconditioned cube. From my experience, you will find the difference. How and when attendees will get your certificate? Yeah, this will be for the Mega Plus. They will answer you about the certificates. And the example of seismic data. Yeah, example of seismic data conditioning. Okay, let's assume that when you are doing seismic, you need to make like the discontinuity to check the discontinuity. So you are going to do variance. Okay, so when you do variance, you will take the seismic as an input. When you have the seismic as an input, sometimes you have some of the noises and some of the data need to be filtered. So it is recommended to do, one of the softwares recommended this also workflow is to do the structural smoothing first, and then after structural smoothing, but of course to take care, you need each time you do conditioning, you need to display the conditioned and the unconditioned before and after in order to see the effect of this conditioning. Sometimes this conditioning, if you make it this like very hardness to do that conditioning, sometimes it may neglect some data. Okay, so you need to eliminate this option and try to eliminate only the noise that you have. Okay, of course the data is not free noise, but you need to make it like we need to make it like decrease this noise as much as we can. So we can do like that one. So you can do structural smoothing first, and then you can do the coherency or variance, and then you can display the result. Try to do the variance without structural smoothing and with structural smoothing and see the results. Okay, and also the anti-track. Try to use the anti-track after smoothing and before smoothing, and you will notice the difference. Moving to another questions. Another question: how do we choose the right seismic attribute for our data and our output? For example, if I wanted to identify fault, or in other case, I have to delineate carbonate reservoirs from my data. Yeah, different answer for these different two stories. Okay, you need to identify faults. Okay, you can go for discontinuity attributes, you can go for curvature attributes, you can go even for RMS attribute. It measures the change in lateral changes, but also it will guide you through the change, because the fault is abrupt change. It's an abrupt change in geology. So you can also notice that the fault. But for the delineate carbonate reservoirs, it depends on the data. Do you have carbonates only, or you have carbonates embedded in let's say clastic reservoirs? So, but anyway, you can go for the carbonates. Of course, you are going to target the fractures of the carbonates, right? Am I right? You are going to track the fracture of the carbonates, not the carbonates itself, of course. So from the workflow that I have said before, you can use the pre-stack seismic inversion to come up with the results, which can be used to calculate the geomechanical properties. These geomechanical properties will guide you through that the most areas that have high fractures, which is others having low fractures intensity. And also we can use the fracture intensity log from the FMI, and then you can take this log and relate this log with the properties of the reservoir, that the area that you have. Then from that you can populate the area and to try to track the high fractured area and low fractured area. Okay, so you can eliminate and try to focus for that one. Even from the seismic inversion, if you go beyond the deterministic and go for the stochastic seismic inversion, geostatistical seismic inversion, even you can use that. You can generate the what we said that it's like a volume, probable volume for carbonates and the probability for the non-carbonates. You see, so you go for further advanced according to the data that you have. So you need to check the data first, is it can be addressed from the simplest way, and then you go for advanced, because I know time is very critical and crucial. You need to finish some of the prospects as much as you can, quickly as you can. So you need to do that and address that in a timely manner also. So we do not have, usually we do not have this list this time. Okay. So after doing the structural smoothing, other attributes would be applied on the structural smooth volume. Yeah, you can use that volume, which is structurally smooth, and you can make like variants. Okay, and after you make the variants, you can take this variance also and make an input, this variance as an input, and try to make the anti-track. So you can do attributes for the for that cube and for even the output from another attribute. Okay, even the post-stack seismic inversion. When you have post-stacks, one of the cases that I have worked on, I have a post-stack only data, so I generated a post-stack seismic inversion, the model-based and the colored inversion, and then I cannot go beyond that one. So you need to use that. Yeah, the screen is blank because I didn't share anything. Just I'm talking with you. The this case is not in the presentation, so I didn't append, but I can share with you in the group also the PDF, which is published paper. So this case, we have like a post-stack seismic inversion, colored and model-based, and then I used that volumes in order to extract some of the attributes from the B impedance itself. So you make like surface attributes for RMS and doing some of these attributes also. It's like a mathematical on the B impedance cube. In order to, we use a mathematical to do like emphasize or make it like amplifier for the amplitude. You see, you employ everything to what you need. So you see your case, what is needed to do, and then when you come up with every result, all the results, you need to amplify or magnify that amplitudes, which is embedded inside the other amplitudes. So we make it like using RMS or doing arc length, the mathematical operations to make it very large and to highlight your attributes only. Okay, minimum or maximum amplitude. So you can eliminate, if you have minimum, so you can take the minimum and then you can eliminate the maximum. So you will be able to see the minimum only. So it depends, of course, I know it's very, very wide, but it depends on the data, depends on the result, depends on what you need to see or to highlight to your colleagues. What are the most commonly used software tools for seismic attributes extraction and analysis in hydrocarbon exploration and reservoir characterization? As I said, the most of the softwares having a lot of having the capability to do some of the extraction. They are very, very, very common. And even if the students also, some of the students in the universities having this license, and some of these softwares are free, like OpenDetect. Some of the modules are free, so you can use and you can try. You can download from the OpenDetect website also. This is very good, very, very excellent software. Some of that software is paid, of course, so you can get that license by contacting the company itself, which is widely used by the industry, like 𝗏𝗏𝗀𝗏, Hamsul Rasul, JSON. All of this is used for the Kingdom also. I'm not need to all of the softwares in. I don't need to forget some of this software paradigm also. So have decision space, all of this, and even all the geoframe, old software which is obsolete now, even used also for using some of the seismic attributes, doing some seismic tool ties and all of this. So to do seismic reservoir characterization, you need some of these softwares. All of the softwares I think do that, but it depends on some of the softwares is more specialized for that one. So you can use the more specialized to do whatever you need. Okay. So do you have any more questions?
Okay. Yes, I think we don't have more questions. So thank you all for attending today's webinar. It was a pleasure having you with us. We especially appreciate Dr. Ahmed for sharing their expertise and for answering all the questions, and also for hosting this wonderful webinar. If you couldn't join us live today, the recording will be available soon, and we'll share the link shortly. We truly appreciate your participation and look forward to seeing you in future sessions. Have a good day. Thank you so much.
Thank you, Mega Plus. Thank you all attendees.
Thank you.